Hello students, welcome to the online lecture class on digital signal processing. We have already familiarized ourselves with the different types of signals, then the difference between digital and discrete signal, classification of different signals, advantages and limitations of a digital signal processor. Then we have also studied about energy functions in our previous theoretical classes. Today I am going to discuss about periodic and aperiodic signals. A discrete time signal xn is said to be periodic with a period of capital N if it satisfies the equation x of kn plus n for all n. Now, in this equation, k indicates a positive integer. The smallest value of capital N for which this equation is true is known as period. In other words, we can also say that period indicates the number of samples after which the sequence repeats itself. For instance, an example of a periodic sequence is as follows. Okay, so this diagram is basically indicating an example of a periodic sequence. Here we can see that the amplitudes of the first sample is at 3, second one is at 2, and the third one is at 1. After this, again the same amplitudes are repeated at instance at 3, 4 and 5. Now, this particular pattern will not be followed in case of an aperiodic signal. Now, let us consider a discrete time signal given by x of n equal to a sine of omega naught n plus theta. Here, theta indicates the phase shift of the signal, omega naught indicates the frequency, and capital A is for amplitude of the sequence. In order to determine whether this signal is periodic or not, it is essential that sine of omega naught n plus theta must be equal to sine of omega naught n plus n plus theta. Now, from here we can say that omega naught capital N must be equal to 2 pi small m, where m is a value of integer. So in other words, we can say omega naught by 2 pi must be equal to m by capital N. Now, it is not at all guaranteed that this particular ratio m by n is a rational number or not. It is essential that for a discrete time signal to be periodic, the fundamental frequency omega naught must be a rational multiple of 2 pi. Only then you can say that the discrete time signal is periodic. Next, we move on to even and odd signals. A signal xe of n is equal to x of minus n in case of an even signal or a symmetric signal. Example is cos of omega n. Now, in case of an even signal, we can observe that the amplitudes of the sequences on either side of n equal to 0 must be equal. So, an example I told you already of cos omega n. So, we can write at n equal to 0, we can have this particular amplitude. At n equal to 1, we can have this as an amplitude. At n equal to 2, this may be the amplitude. So the same thing will be repeated here again, but with just the negative number. So here x of minus n means at the instant minus 1, this must be equal to the amplitude at n equal to 1. Then at n equal to minus 2, again you can find that this and this samples are having the same amplitude. So this is an example of an even or a symmetric signal. Now for an odd signal we can say x of n xo of n must be equal to minus of x minus of n. An example of this signal is sine of omega n. So here we can see at n equal to 0, this is the value. At n equal to 1, let this be the value. At n equal to 2, let this be the value. Correspondingly, for the signal to be an odd signal, at n equal to minus 1, the amplitude will be present but in a negative direction. So for the other one, this will be present at n equal to minus 2. Okay. Next, we move on to operation on signals. So the first operation that we will learn today is the shifting operation of a signal. This operation will be taking in the input sequence and shifting the values by an integer increment of the independent variable. This may either delay the sequence or it may advance the sequence. Mathematically, it can be represented as y of n equal to x n minus k. Okay. So for instance, if we have the following discrete signal as this. So this is the sequence. So a delayed version of this will be, instead of starting at the instant n equal to 0, this signal may start at, let us say, n equal to 3. So for 0, 1 and 2, this will be absent. For 3, it is having the magnitude 2. At 4, it will be having the magnitude 1. At 5, it will be having the magnitude 2. Okay. So this is an example of a delayed version. In case of an advanced version, instead of starting at n equal to 3, it may start at n equal to -1 or n equal to -2 and so on. The next type of operation is time reversal. Time reversal operation. Now this operation can be obtained by folding the sequence about n equal to 0, or you can say simply by flipping over. It is denoted as x of -n. So here, as an example, I can show you. Let us say we have a discrete signal. We have it at -3, -2, -1 and 0. Let this be the amplitude 1, amplitude 2. Here also we are having an amplitude 1. And then again we are having an amplitude 2 over here. Okay. So let us say if I want to shift this signal, or let us see if I want to reverse this signal, then simply I have to flip it over. So flip it over means this same signal, if I want to shift by, let us say, if this is x of -n, if I want to shift it by x of -n -2. -n -2 means, that means the signal, instead of starting at n equal to -3, it should start at n equal to -3 -2, that is -5. So at n equal to -5, the first sample value 1 will appear. Then at n equal to -4, the next sample value 2 will appear, and so on. So I can write it as -5 -4 -3 -2. So here amplitudes 1, 2, 1 and again 2. Okay, so this is an example of x of -n -2. Next operation is time scaling operation. Now this is obtained by replacing small n with lambda n in the sequence xn. So if we have lambda equal to 2, then we get a new sequence y of n equal to x of 2n. Okay, so we can write it as, if we have an example of, if I consider let let us say this is amplitude 5 x of n for n equal to 0. Then we have 4 for 1. Next you have 3 at 2. Next we have 2 at n equal to 3, 1 at n equal to 4, and so on. Okay. So that means if this is my signal xn, then as per this formula, yn should be equal to x of 2n. So I can have y of 0, this will be equal to x of 0, that is equal to 5. Then y of 1 will be equal to x of 2, that will be equal to 3. Then y of 2 will be equal to x of 4 because it is 2n. So whatever the value over here, that is here it is equal to 1 and so on. So the new sequence will be this will be the sequence y of n. 5 will be the first for 0. Then y of 1 will be equal to 3. So if I consider 3 over here somewhere, so this will be y of 1. Y of 2 will be equal to 1. And so on. Okay, I hope it is clear. Next we move on to scalar multiplication. Here, a signal xn can be multiplied by a scale factor a or alpha. So if I have the signal as xn, then this will be multiplied by a scaling factor, let us say a. In some books you may find it as alpha. This is equal to yn. So yn is basically equal to a into x of n. So if the sequence for the signal xn is equal to 1, 2, 1, minus 1, this is just an example. Then I can say the signal a into xn will be equal to, so it is a into xn, right? So the value of a has to be said. Let us say a is equal to 2. Then this will be 2 into 1, 2, 2 2s are 4, 2 into 1, 2, 2 into minus 1, 2. Okay. Next operation that we move about, that is known as signal multiplier. So suppose we have two signals, let us say x1n, we have another signal x2n. To indicate multiplication, it is indicated as this, result is, let us say, a new signal yn, which is the product of x1n and the signal x2n. Now what happens exactly in this signal multiplication? In case of this multiplication, the corresponding samples of the two signals x1 and x2 are multiplied. So if the sequence of x1 n is equal to, let us say, -1, 2, 3, -2, and the sequence for the signal x2n, this is equal to 1, -1, 2, and 1, then the new signal y of n will be the multiplication of the corresponding sample. So -1 into 1, this will give you -1, 2 into -1 will give you -2, 3 into 2 will give you 6, -2 into 1 will give you -2. Okay. In case if both the sequence are of unequal lengths, then zeros will be padded to the sequence containing lesser number of samples. That means, let us say the number of samples in x1n signal is 4 and the number of samples in the signal x2n is only 2, 1 and -1. The remaining 2 are absent. Then how will you perform this multiplication? So in case of these two in case of this sequence with less number of samples, we will consider zeros instead of 2 and 1 respectively and complete the multiplication process. The last operation that we are going to discuss today is that of addition and subtraction operation. Addition and subtraction. The symbol for performing addition and subtraction is this. So we have a signal x1n. We are performing addition of another signal x2n with this. So result will be a new signal y of n, which is the summation of x1n plus x2n. Okay. Now, if you are performing subtraction, to indicate that a negative sign must be given. That means if you want to perform x1n minus x2n, then there should be a negative symbol associated over here. In case of addition, it is not necessary to place this particular symbol. So here also, just like in case of multiplication, the corresponding samples will be either added or subtracted, depending upon the type of operation that you are performing. Now you must remember that in a digital signal processor, in a digital hardware, we cannot add more than 2 numbers at a time. That means in an accumulator, we are basically feeding the numbers in a sequence and they accumulate over there. So for adding 3 signals, 2 summers must be involved. Okay. So that's all for today's lecture. We will again continue with our classes in the next online session. Thank you.